Okay, so in this lecture, we're going to talk about functions of invariables. And so these functions look like f, and they map elements from R in to R. So the domain elements for these functions are vectors. They're ordered tuples of real numbers. So these functions take as inputs in vectors. Okay. And these functions surprisingly obey many of the rules that we know about functions of a single variable. So many of the same rules as functions of a single variable. And I should also say, in this context here, I should also maybe emphasize that the output is a scalar. Because there are functions that output vectors, or functions that output any number of things. But for our purposes now, we're just looking at functions that take as input vectors and then spit out some scalar numbers. Now, to best illustrate how these functions are really just, they're very similar to functions of a single variable, we're going to look at one example and we're going to focus on this example for a few minutes. So we're going to say let f that R2 R, so it takes as input two-dimensional vectors. Let this be defined by z equals to f of xy equals x squared plus y squared. I'm going to focus on this function here. Now, the notation is a bit annoying, but it's the x and the y will become apparent when we look at trying to plot this thing. But in general, you should realize that this function is maybe the same thing as saying f of x equals to x1 squared plus x2 squared. This is the vector notation for that function. This is the variable notation for that function. They mean the same thing. But we're going to use this notation to kind of help us get an idea of what this function does, how it behaves, and how we can visualize it in space. So in order to understand this function, in order to understand f, we can fix one of the variables. So we can fix either x or y, and then vary the other variable or variables if you have more than two, vary the other variable, all the while observing how f changes. Okay. So, for example, we have the z, which is just a representation of the function f, is equal to x squared. So what we can do is we can just say, we can fix y at 0. So just fix y to be 0 and see what happens. So if this is x and this is z, and we choose varying values for x, how is z going to behave? Well, the output is just the parabola, right? Okay. Also, when y is equal to 0, and we're looking at maybe rates of change for z as x varies, right? So as x varies, how does z change when y is fixed at 0? Well, note that dz dx in this case is equal to 2x, right? So the derivative of z with respect to x tells us the slopes of the tangent lines, just as before, and it tells us the rate of change in z as we vary x. Okay, well, that was when we made y a constant. What about when we make x a constant? Right, so we just set x equal to 0. Let's see how z behaves as we vary y now. And again, this is just going to be a parabola. So y, z, and as we vary y, we're just going to have another parabola like that. Okay. So, and again, if we wanted to look at the rate of change for z as we vary y when x is fixed, then if we look at the derivative of z with respect to y, it's just going to be 2y, and that again will give us the tangent lines. It'll give us the rate of change in z as we vary y. It'll give us everything that we know from just regular calculus of a single variable, right? So what about when maybe, what about when z is equal to x squared plus, and what about when y is equal to 1? Well, then if we plot this again, so here's x, here's z. If we plot this, then it's a parabola raised up by 1. Okay. And how does the behavior of z change as we vary x? Well, we take the derivative of z with respect to x. That's just a constant number, so that goes to 0, and we have 2x. And we see that the derivatives are going to be the same when we take the derivative with respect to x, because the y variable is just a number, and it goes away when we take the derivative. The derivative of a constant is 0. And then we can do the same thing over here, right? So we can say z is equal to 1 plus y squared now. So now we've fixed x at 1, and we're going to vary y, and we get the same exact, it's kind of symmetrical in this case, but it's just the parabola raised up by 1. And again, the derivative with respect to y of this function is still 2y, because this is a constant and it goes to 0. So the key takeaways here are that you can fix all variables except for 1, and then vary 1, and you can get a sense of how z behaves with respect to that 1 that you're varying. And because of this, because you can treat it as a function of one variable, if you treat the other variables as numbers, we can use all of the same rules from calculus of a single variable piece by piece on the various functions that you get. You can think of this as like two different functions, one varying in x, one varying in y, and then together, what do they make, right? So in particular, if we wanted to somehow get a picture of that function here, right? We can use a three-dimensional coordinate system, which is really a pain to deal with, but it can sometimes give us information about the function in question. So you start by drawing your z-axis here, your positive y-axis here, and your positive x-axis here. And negative x, it's kind of shooting back into space, and negative y is going that way, and then below this plane is negative z. And every point in this plane, if you pick a point in this plane, it has a x value, a y value, and a z value. So like that would be maybe x went to like negative 10 or something, and then y like +3, and then z like up 2. So it could be like negative 10, 3, 2, and that's a point in space. Okay, so this is a three-dimensional plane. This space is altogether R3 though, which means that each point in here represents a vector. So like that's a vector, so forth and so on. Okay. So, but when dealing with this function now and trying to picture it, we can use this space to get an image of this. In particular, I know what this one looks like. When x is 0 and we vary y, z looks like that. So we can make x equal to 0 and vary y, and we get this perfect, we already know what it looks like. We know that's a perfect parabola like that. Okay, so that's when we fixed x at 0 and we varied y, that's the parabola we got. But we also know when we fixed y and varied x, so like this way, we have a parabola like here, right? Coming out this way. So as x increases, maybe like that, and then so it looks like this blue line here would have been behind, right? So and the red line is in front. And then behind it, like that. Okay. And then the same thing applies for everywhere else, right? Like when we make y is equal to 1, right, and we vary x, or we make x equal to 1 and we vary y. So we make x equal to 1 here and we vary y, we have the parabola raised up by 1. So it's like up here now. So like that. But altogether, when we start combining all of these, we get this like whole thing that is a surface in space. So the graph of functions of two variables is a surface in space. Okay. And these surfaces are just values of z. That's all it is. And the input, your input for anything on this surface is a vector in xy, in the xy plane. for example, like this point here, that's like when x is equal to 2. So 2 squared is 4 plus 1 is 5. So, and then y was 1, right? We fixed y at 1. So at 2, so at 2, 1, so that's the vector 2, 1, there, the corresponding value for z would have been 1, 2, 3, 4, 5. So that point right there on the surface, this would be f of 2, 1 on that surface, which took as input this vector and then put it right there. Okay. So now you should be okay, somewhat comfortable with the idea of that surface based off of fixing one of the variables and varying the others. So we also want to know where to move on this thing. How does z change as we vary x and y, right? Well, think of it the same way as we did over here. When x is equal to 0, right? When we fix x at 0, we're on this curve, right? So if we point out right here, so this would be like the vector 0, 3 or something. Well, we can determine if we're going to go up or go down if we move this way or that way by just taking the derivative with respect to y, and we'll get the slope of this line, right? So this is like dz dy of 3 when z was equal to 0 plus y squared. So when z was a function of just y and we had 0, x fixed at 0, we just take the derivative of this with respect to y, plug in 3, and it'll give us the slope of that line right there. Okay? And if we wanted to know if y is fixed and we vary x, then we would take the derivative with respect to x for the function z, and then we have the rate of change that way. But there's all sorts of combinations of fixing one variable and moving the other one. You can fix any number of x's and vary y, fix any number of y and vary x. In order to get the full information about what changes, right? Like this is measuring the change when y increases, right? Or at this point here. But they also, if we fix y at 3 and then we vary x, there's going to be a change in the x direction. Well, there's going to be a change in z according to the x direction. So how do we put all those things together and understand change this way versus change this way at the same time? Well, obviously, we're going to need two different numbers. The number in this direction is measuring the change in z with respect to y. The number in this direction is measuring the change in z with respect to x. Both of these are derivatives, simple single variable derivatives. But to distinguish from single variable derivatives to multivariable derivatives, we introduce notation. And the notation that we introduce is that of the partial derivative. Okay. So the partial derivatives of f of xy are the functions given by this. So notice over here that whenever we fixed the other variable and we took the derivative with respect to the other variable, those constants, they just went away. We have the same derivative with respect to x every time. Well, we just have to do that formally and just write it out as del f. So this del f is different than the d, to emphasize that this is a partial derivative. So this is the derivative of f with respect to x, and that's going to be the limit as delta x goes to 0 of f of x plus delta x comma y minus f of x comma y over delta x. Now again, if you think about just fixing y is equal to 0, we did exactly that here. This is just the definition of the derivative, right? If you look back at your calculus notes, that is the definition. If you just got rid of the y, that'd be it. So del f del y now is the same thing, just with respect to y. So now we're fixing x, and now we're varying y. And these limits, if they exist, obey all the same rules from single variable calculus. Which is really, really nice. Because all the things you learned with single variable calculus, everything that you know applies here as well, and looking at the partial derivatives on their own. Okay? Now, if you think back to the derivative of a single variable function like we had here, is fixing the other, as we have done, as I keep on repeating myself on, you take the derivative and then you plug in an x, and it tells you at that x what the rate of change is, the instantaneous rate of change, that nonsensical thing, right? But we want to know if you plug in an x and a y at the same time, how much are we changing in x, how much are we changing in y at the same time, right? So we do that with a vector, okay? And that vector is called the gradient. So this is Greek letter nabla of f, and this is a function of x and y. This is a not a scalar value function, it is a vector value function. You input x and y, you get out another vector. It doesn't produce a scalar, it produces a vector. And the entries in that vector are your rates of change in the x and y directions. And so how would you do that? Well, that's just going to be partial f, partial x, xy, and then df, dy, xy. So now if you give me any point in the plane, anywhere anywhere, right? For example, that point 2, 1. And I want to know if I go x, how much is z changing if I go that way? If I go y at that point, how much is z changing if I go in that direction, right? So this is measuring where we are on this shape, right? Just think back to when x was equal to 0 and we varied y, and we had this blue thing right here, right? That perfect parabola. And if we're here, right, and we took the derivative with respect to y here, we'd see that there's a positive tangent line there. Okay? So we know that if we move y positive, we'd be going up at that point. But what about if we move x at that point? Well, if we move x, would we be going up or down? Okay. So we should say that we plug in an x and a y, we get a vector, and wherever that vector lands, like here or something, wherever it lands, it will tell us or point towards an increase in z or in f. If we want to have bigger z, we go in the direction of that gradient. I mean, of the gradient, which is a vector. We go in the direction of that vector. So we head that way, and we're going to be going up or something like that. And again, I hope that this like piece by piece, you're understanding that the derivative is just in each of the components of that vector, which it's kind of combining everything about wiggling around the variables and seeing what happens to the output z. Okay. Now, I have focused on a function of two variables because we can picture it. I made it a rather simple function so we could look at the parabolas. But in general, you can have more than two variables. You can have n variables, and the same rules will apply. In particular, for a function that takes as input n-dimensional vectors and outputs a scalar, the partial derivative of f with respect to the ith entry of the vector is just it's gross to write out, but I guess I have to now. So it's just the difference quotient again. Dot xi plus delta xi dot xn minus f of x dot to 1 right there, xn all over. It's the same idea. It's a messy formula, but again, the partial derivatives obey all of the things from single variable calculus. So all this is saying is fix every other variable to be 0 and then take the derivative of your function with respect to that entry, xi. And also, the gradient is the same thing. Nabla f of the vector x is just del f or df dx1 dot all the way down to df dxn. Your input or n-dimensional vectors. Okay. Okay, so that will conclude our brief discussion on functions of invariables, partial derivatives, and the gradients. We will come back to this in a lecture down the line.